Before going into the detail, let us determine some convention. By p 2 pi, we mean the set of, well, it may not be a set actually, but a collection of all functions with period of 2 pi. Okay, so all the functions we discuss will be elements of this set. Actually, in addition, we also assume that the functions in this set are continuous. Continuous, except for finitely many points. Except for finitely many points. So it can be discontinuous, but the point of discontinuity is at most finite. So not countably infinite or uncountably infinite. It's just finitely many discontinuous points. And next we define R 2 pi 1. So this is another set of functions so that belong to p2 pi. So they have a period of 2 pi and number of discontinuous points is finite. And also they are also absolutely integrable. Okay, that means the integral from 0 to 2 pi of the absolute value of this function is finite. So this means absolutely integrable. Actually, it's Riemann integral, integrable, what is what we mean. So this R stands for Riemann. So this means Riemann integrable. And similarly, we define R 2 pi 2. So this is again a subset of p2 pi, but in this case, the functions should be square integrable. So that means f squared is integrable. Okay, so this means square integrable. Well, if you already know Lebesgue integral, then you can just replace this with L1 integrable and this with L2 integrable. But in this lecture series, I do not assume the knowledge of Lebesgue integral, so we just stick to this notation with Riemann integrals. Now, actually, this R2 pi 1 and R2 pi 2, they are related. And in fact, if a function belongs to R2 pi 2, then that implies the function also belongs to R2 pi 1, not vice versa in general. And this can be proved by using the Cauchy-Schwarz inequality. Schwarz inequality. So that is if we have this integral, the absolute value of f of x. So this can be considered as this function times 1, and 1 is a constant function. So by applying the Cauchy-Schwarz inequality, this is less than or equal to the square root of the integral 2 pi and the square of the function dx times the square root of this 1 squared dx. Okay, so if this is finite, then this is finite. But this being finite indicates that the function belongs to R 2 pi 2. So this holds. Okay, let's see an example. Consider this function, f of x 1 over the absolute value of sine x to the power of alpha, where alpha is a constant that is positive. And we can show that if alpha is between 0 and 1, then f belongs to R 2 pi 1. So f is a periodic function and that is absolutely integrable. And if the value of alpha is between 0 and 1 half, then the function belongs to R 2 pi 2. So if alpha is greater than half and less than 1, then it belongs to R1 but not to R2. And you should know that this function is not continuous function on the interval between 0 and 2 pi, but there are some discontinuous points such as x equal to pi half, for example. But those discontinuous points are just finite. And actually, I think there are only two such points. So except for those points, this is continuous. And since we are taking this absolute value, and also this is periodic function, so we can consider this integral, let's say absolute value of f of x. As by symmetry, we can reduce this integral to from 0 to pi half and times 4 of this 1 over sine x to the power of alpha and dx. So this integral is reduced to this integral. Now we can express this function, this integral, in terms of the beta function. In case you have forgot, beta function is defined as this. Beta of p q is equal to integral from 0 to 1 x to the power of p minus 1 and x minus 1 minus x to the power of q minus 1 dx. And this p and q should be greater than 0. And by using the beta function, we can calculate some integrals involving sines and cosines. So sine to the power of a, theta, and cosine to the power of beta, d theta, can be expressed in terms of the beta function, this one. And I think we have shown this before somewhere. But anyway, I just list the formula. That's this integral becomes 1/2 times beta of a plus 1 over 2 and b plus 1 over 2 when alpha a and b are greater than -1. Now, using this formula, let's express this integral. Okay, so between 0 and pi half, sine x is positive, so we can just consider this. Okay, so let's see. So for integral sine x to the power of negative alpha, so this is negative alpha, and cosine x to the power of 0. There's no cosine here, so that's 1 dx. So this should be, apply this formula. So 1/2, so we have 4 here, so that should be 2 and beta function, and a is negative alpha, so that will be 1 minus alpha over 2, and b is 0, so that's 1 over 2. So that means as long as alpha is less than 1, so if alpha is less than 1, and of course assuming it's positive, then this integral is finite. And similarly, let's calculate the square of this function. So f of x squared. So that becomes this integral, and sine x to the power of negative 2 alpha here. So that becomes 2 beta and 1 minus 2 alpha and 1 over 2. So this is finite if this is positive. So that means alpha is less than 1/2. So actually alpha is assuming alpha is positive. So as long as this is satisfied, then this integral is finite. So it is square integrable. Otherwise, these integrals diverge, so we see that this conclusion is correct.